The universe never fails to surprise humankind with stunning, incredible facts about its nature. It is literally crammed with mysterious objects and fascinating phenomena. Imagine a star against which the sun would look like a tiny sparkling speck in infinite space. A star so large it would be able to absorb most of the solar system. A celestial object of dimensions whose values would urge us to question the feasibility of this star's existence. It has shunned the intrusive gaze of many a curious observer for many years, and only recently has it revealed some of its mysteries. Until a short time ago, it was UY Scuti that used to be considered the largest star known to mankind for a long while. Located 9,500 light-years away from the Sun, the star is so staggeringly enormous that it would cover areas beyond Jupiter's orbit were it placed in the center of the solar system. Its radius may reach 1,900 those of the Sun, and its volume may be over 5 billion times that of the Sun. However, recently a new giant has claimed the title of the largest star in the known universe. It is known as Stephenson 2-18 or RSGC 2-18. The star lies approximately 20,000 light-years away from the Sun and is part of the open cluster Stephenson 2, although according to some scientists, this space object should not be associated with the Stephenson cluster as it wouldn't be accurate. Either way, Stephenson 2-18 is located in the Scuti constellation and continues to bear its original name. The star itself was catalogued in the All-Sky database back in the 1990s, but giant clouds of cosmic dust largely interfered with observation of the star clusters in the Scuti constellation, obscuring them from any observer anxious to find out more. Only in 2020 were scientists able to acquire data about its size, and the information proved to be astonishing. According to some estimates, the radius of Stephenson 2-18 may reach up to 1.5 billion kilometers, which is 10 times the distance from our Earth to the Sun, or 2,150 times the radius of the Sun. This means that the supergiant's volume should be about 10 billion times that of the Sun. Placed in the center of the solar system, Stephenson 2-18 would easily swallow up Saturn, along with all of its rings and moons, to say nothing of the terrestrial planets. Interestingly, it would take light almost 8.5 hours to travel the length of this gigantic star's equator. This is the same time it takes sunlight to reach Pluto at the remotest point of its orbit. The supergiant's luminosity is estimated to reach 440,000 times that of the Sun, although its surface temperature is comparatively low at about 3,200 Kelvin. This is about 2 times as little as that of the Sun and corresponds to the red band of the light spectrum. This is the reason why Stephenson 2-18 falls into the category of red supergiants. Also, this relatively low temperature implies that most of the star's radiation is in the visible and thermal spectra, with amounts of deathly ultraviolet and X-ray types of radiation rather negligible in comparison. It may seem strange that in spite of its impressive dimensions and sufficient luminosity, Stephenson 2-18 cannot be seen from the Earth with the naked eye. But this has to do with its low surface temperature as well as clouds of stardust and gas shrouding the giant star, thus concealing it from observers on our Earth. They absorb and disperse the star's light, and this poses difficulties for studying the object. The mass of Stephenson 2-18 still remains to be gauged. However, supposing its inner makeup is similar to that of UY Scuti and other supergiants, it should be anything within 20 solar masses. If it is the case, the average density of supergiants like that must be extremely low and almost equal to the density of the Earth's atmosphere at a height of about 90 kilometers above the sea level. That is practically on the border with space. It is really amazing that thermonuclear energy, that is the kind of energy that gives a glow to a star, is still sustained in such conditions. Supergiant sizes are so mind-boggling that these objects are hardly steady. Most of them are variable in terms of their luminosity, and as a rule, this variability is unpredictable. No wonder, as the overwhelming majority of supergiants are in the final stages of their life cycles, which means that they may go supernova literally at any moment. According to the contemporary scientific concepts of stellar evolution, it is stars with original masses from 10 to 40 that of the Sun that qualify to become red supergiants at a later stage of their existence. Thermonuclear reactions in their interior rapidly burn out all hydrogen, thus turning it into helium. After that, fusion reactions of helium, carbon, oxygen and lithium become the chief energy source of the star. Life expectancy of stars of this kind is comparatively short, just a few million years. As it evolves, the prospective supergiant rapidly expands in size and loses its mass on account of strong solar wind. Clouds of stardust and gas surrounding the original star are quickly absorbed by the new star, which keeps swelling way beyond its original size at an astonishing rate. However, its own solar wind creates a new nebula around the star. On account of the short lifespan of this kind of star, no planets can realistically originate in this nebula. Eventually, the supergiant explodes. Following the supernova or even hypernova event, the outer layers of the star are hurled away and then gradually cool off, forming a nebula. As for the former core, it becomes either a neutron star or a black hole depending on its mass. By the way, feel free to see our previous videos about dwarf stars and supernovae. A hypernova event is accompanied by a high-energy X-ray burst, powerful enough to eliminate any life within the radius of several light-years. Luckily for us and the Earth, all supergiants identified by scientists so far lie considerably further than that, so we seem to be safe from those. Due to active radiation of charged particles, the rotation of stars of this type gradually slows down, and eventually their outer layers practically grind to a halt. The core of the star, meanwhile, continues to rotate quite unabated, and there may be a substantial difference between the speed of the core and that of the outer layer. Taking into consideration the high luminosity, low temperature and impressive dimensions, on balance, it is safe to assume that the habitable zone of Stephenson 2-18 should be really huge. Its middle should lie approximately 663 astronomical units away from the star's center. In other words, 20 times the distance from the center of the Sun to Pluto's orbit. And as for the area of the habitable zone, it is expected to be 1 billion times that of the Sun. Scientists do admit of the possibility of the existence of planetary systems around supergiants. But what with these stars' short lifespan and unstable conditions, the chances are almost negligible. At any rate, no confirmed exoplanets have so far been discovered in the environs of one. Stephenson 2-18 lies so far away that its light travels to our Earth for 20,000 years. For all we know, at this very moment its core might be shrinking to form an extremely dense neutron star, with red-hot shards of outer layers flying away in all directions to become part of ice-cold space. But mankind will be able to find this out only in a very distant future.